So I believe there is a shift now from initially the community was guided by particle physics principle, because as soon as people realized that dark matter was motivated by, at least had possible implication for particle physics, people actually let themselves guided by particle physics principle. Now that we don't see any new particles at LHC, for example, then the question is, where do you find evidence of dark matter? And that's basically just in the universe. So you should use cosmology instead to guide your principle to find dark matter. And so I guess the question now is how robust, you said the evidence are very robust, but how important those observations are. What can they teach us, for example?
So yeah, well, so that's somewhere where we're constantly pushing the envelope, and actually, for as long as the particle is not detected, then doing the hard work of pushing to ever tighter constraints on dark matter particle properties is worthwhile. And so we've entered an interesting regime where when you think about what dark matter is, I talked about the cosmic microwave background radiation evidence for dark matter. But this is very, very large scale evidence. So this tells you that there's dark matter. It tells you that it's non-baryonic. It tells you that it doesn't interact with photons, but it really doesn't give any kind of differentiating power between the different kinds of models that you were discussing. So sterile neutrinos are fine as far as the cosmic microwave background is concerned, as are neutralinos, as are axions, which we haven't discussed, and a whole bunch of other models. If you want to start to unpick these different possibilities, then one way to go is to try and measure the distribution of structure in the universe on ever smaller scales. And it's on these small scales where you start to see the effects because, for example, if you have a very light dark matter particle, then early in the universe it has a period of relativistic expansion. It's what's called a relativistic fluid for a time. And while it's expanding like that, that suppresses the growth of structure in the universe. And so in the early universe and on small scales, the dark matter is not able to cluster into little blobs. Only later on is it then able to, as it expands and effectively cools, it's able to start collapsing and form structures. So this then manifests in what you see in the universe as less small galaxies in the early universe. And that's something we can actually go and look for. It's difficult because we're looking for the very smallest things in the very early universe. And because when we look in the early universe, in some sense we're peering backwards in time, those photons of light emitted by the first galaxies have to travel across the whole universe to get us to us today. So when we're talking about the early universe, we're talking about observing things that are very, very distant, and we want to find the very smallest things, and so they're very, very faint. And so one way to do this is to literally try and directly see the photons of light from these tiny galaxies forming at the beginning of the universe. But this is very challenging, even with the latest modern telescopes. So a very popular field has emerged, taking a slightly different approach, which we call near-field cosmology, or sometimes referred to as sort of galactic archaeology, which is basically saying if these tiny galaxies were born at the beginning of the universe, some of them might survive through the whole universe without encountering another galaxy or being gobbled up, and then literally live in our cosmic backyard today. And these are tiny, what we call dwarf galaxies, and this is my own area of expertise, is trying to hunt and find these tiny dwarf galaxies and use their properties to make inferences about the nature of dark matter. And the idea is basically the same. We're looking for evidence of very small scale growth of structure, but instead of trying to look for it right back at the beginning of the universe directly, we're looking for the bits and pieces left over from that early time that live around us today. This is sort of beautiful that nature gives us this information, but it's much more complicated to interpret this information because we then have to have a model, theoretical model, that takes those tiny galaxies from the beginning of the universe and correctly evolves them through 14 billion years of evolution to the present day to allow us to make inferences from what we see. And that is where there has been a sort of substantial battleground, if you like, a lot of conflicting views on what these galaxies are telling us. But personally, I believe there is now an emerging consensus that the sort of standard model of a non-relativistic, non-self-interacting particle seems to be consistent with all known data at the moment. Now, that doesn't mean that other models are not. So what we are now trying to do is to constrain or rule out some of these other possibilities. And using these kinds of techniques, we can now make statements, for example, that if dark matter is produced thermally in the early universe, then we can put constraints on its particle mass, that it must be bigger than somewhere between 2 or 4 kiloelectron volts. And that already starts to rule out some models, but not all sterile neutrino models, for example. And we can take this further. If we can find more small galaxies, who knows where the limit lies? I mean, the smallest galaxy we found today so far has maybe 1,000 stars in it, in the entire galaxy. You can compare that to the Milky Way with its 100 billion stars, 1,000 stars. Maybe there's a galaxy with 100 stars, or a galaxy with 10 stars. And if we can find those sorts of systems, particularly if we can find them far away from any other galaxy in isolation, which makes them much easier to model and to understand, then we can really start to put very interesting and competitive and exciting constraints on this temperature scale of dark matter, and therefore the particle mass and its production mechanism, and so on. And this may help particle physicists to know where to look.
Yes, I would completely agree with that, because, for example, if you have some particles with interactions and a mass that is not a few keV, but a few MeV, so like an electron, you still have an impact on our cosmic neighborhood. You can still see their imprint, even though their interaction happened in the early universe, and you think that you have no way to access this, it does change the environment in which we live. So it's clear that by looking at very small galaxies, you will learn a lot about the dark matter properties. But I guess the question is, how much fine-tuning do we have in the observations themselves? I mean, how much fine-tuning do you need at the moment in the main paradigm to explain the formation of these little galaxies?
Yeah, so I think that's a very interesting question, because also, I mean, it's a very different use of fine-tuning. So there's fine-tuning in the sense we were talking about before, which is that in the fundamental physics model, how delicate is the requirement for particular particle masses or interaction cross sections. If we have to have those numbers be right to 1 part in, say, 120 significant figures for the model to work, then that's very disturbing from a theory point of view. But you're absolutely right that there's a second kind of fine-tuning. Which is that, let us suppose we know all the laws of physics, we've got it right, but we want to understand the way the universe looks. If you want to understand the growth of structure, for example, one tool for understanding that, it's almost a necessary tool, are numerical simulations, because the growth of structure very quickly becomes a nonlinear process. You have many different forces to worry about, gravity, electromagnetism, and so on. And so what we tend to do is we start somewhere around the beginning of the universe, which basically means sometime after the emission of the cosmic microwave background photons. We kind of know what the universe looks like at that time from the CMB, from the cosmic microwave background. We put all that into a computer, try to solve the forces of gravity and hydrodynamics, and evolve the growth of structure through to the present day. But we cannot do that perfectly. We cannot model in that simulation every atom in the universe. So even though we may know what the laws of physics are that we should write down and solve, it's just not practically possible. It's an engineering problem, if you like. So we make approximations. And those approximations introduce effective parameters, phenomenological knobs and dials, if you like. And if we have to turn those to very fine-tuned settings to get the theory to work, then that could be an indication that we're fooling ourselves, that the theory doesn't really work, and that we're really trying to diddle the knobs and dials to make things work. And I think for a long time we've been in this slightly frustrating cycle of things where the spatial resolution of these simulations wasn't much smaller than the typical size of one of these tiny galaxies we're interested in. And as long as that's the case, you're not really resolving the physics of the formation of these galaxies, and so you can almost get whatever answer you like. So the models are not particularly predictive, and it's difficult to, you can match all the data, but it's difficult to interpret what that means. And I believe we're now entering a sort of paradigm shift due to improvements in both computational hardware and in software algorithms, where we can reach a spatial scale of about 10 light years. And this is a significant spatial scale, because yes, there's lots of stuff below that scale that we're not modeling correctly, but this starts to approach the typical size of star-forming regions in the universe. And so the simulations still have to be calibrated. They still have free parameters, but we can now select those free parameters to match what we know about star formation rather than what we think we know about galaxy formation. And this is a whole new world, because it means that basically we put into the simulation what we think we know about star formation. The galaxies should then emerge correctly. And this makes the simulations far more predictive. You can actually form galaxies that look like real galaxies. They come out looking like real galaxies, but we haven't tuned the simulations to make them look like real galaxies. We've simply said, let's put in what we know about star formation, what we know about star-forming regions in the universe, and see if the galaxies come out right. And it seems, for the time being, that they really do. And the really interesting thing that comes out from those simulations, which is something I'll talk about a bit in my talk tomorrow as well, is that in the process of forming these realistic galaxies with this sort of spatial resolution, it seems that what naturally occurs in the simulations is the dark matter is heated up. And so what do I mean by that? Basically, you can think of dark matter in these galaxies as having some sort of kinetic energy. Okay? The dark matter particles are whizzing around in the gravitational potential of the dark matter and the stars and the gas. And the faster they move, the deeper the gravitational well. They have a sort of temperature set by that kinetic energy. Now, for the very smallest galaxies, the ones where you get the most constraints on the nature of dark matter, these gravitational wells are quite shallow. And so, as stars form, at the end of their lives, the most massive stars, the O stars and the A stars, they return a lot of mass, metals, and energy and momentum to the surrounding interstellar medium. And this happens through both stellar winds, stellar radiative feedback, and also through supernovae, exploding stars. And this returns energy and momentum to the interstellar medium. And what this does is it causes the gas in the interstellar medium to be pushed around. And that leads to a fluctuating gravitational field. Because you could imagine you have a big gas cloud forming stars, and then the gas cloud is dispersed and blasted out of that region by this energy input from the stars themselves. And as that gas moves away, there's suddenly a lot less gravity in that region. And although the dark matter only interacts with the gas and stars by gravity, they see that loss in the gravitational field and respond. And this causes the dark matter kinetic energy to go up, their orbits are pushed outwards, and the dark matter distribution in that galaxy is altered. And this is very important because this process of dark matter heating seems to be able to explain a wide range of very puzzling observations about these tiny galaxies, which we've known about for nearly 2 decades, and that really didn't seem to fit the standard model. And these are sort of almost, if you like, a third kind of fine-tuning, but very strong correlations between the distributions of dark matter and the distributions of stars. They're very puzzling correlations that you wouldn't expect to see, because you don't normally expect the dark matter to interact with normal matter in any way. So how would the dark matter know to arrange itself in this very correlated state with the stars and with the gas? And this dark matter heating mechanism, which emerges naturally from these new generation of simulations, naturally produces exactly these kinds of correlations. And so I believe that we're now able to make predictions for the distribution of dark matter for a given model, even including these complicated processes. And these new generation of predictions are giving a remarkable match to the data, and will hopefully allow us to really tighten the screws on different kinds of dark matter models in the next few years.